Thanks, John, and thanks everybody for allowing me to present today. Still seems really strange to hear Chris Roebuck from NI, I have to say. So let me, in the interest of bandwidth, stop sharing my image. So this afternoon, I'm going to be presenting for the next, around the next 45 minutes or so. I'm going to be giving an introduction to DQMH. A four-letter acronym that has become extremely prevalent within the LabVIEW community. So hopefully some of you have heard those 4 letters before, DQMH, but I'm sure there's some people in the room. This is hopefully new and interesting and informative content. So just to introduce myself, as John said, my name's Chris Roebuck. I'm Chief Technical Support Engineer at NI. For the EMEA region anyway, and I've been with NI now for just over 14 months. I'm definitely the new boy at NI, but I have been around the LabVIEW community for quite some time. I started as a physics undergraduate, actually working with LabVIEW. Not too far from where I think you guys are today. I was actually based in Warrington at the Daresbury Research Laboratory. That's actually where I started using LabVIEW around 1994, so quite some time ago. Certified LabVIEW architect, test stand architect, and prior to joining NI, I was a LabVIEW champion. But of course, we have to relinquish that title when we join the mothership. In terms of kind of my background, I've worked with a variety of different industries, and ranging from volume electronics manufacturing, that government research laboratory that I mentioned, spent a lot of time doing space and RF electronics and some mil-aero stuff. And you'll see there around the 2012 mark, I worked with Fabiola at Delacorp for about 3 years. So DQMH is a topic very close to my heart, something that I'm particularly interested in. Since then, I've worked with a number of alliance partners, or a alliance partner, and joined NI last year. So let's get started. What will you get from this presentation? Well, we're going to talk a little bit, before we dive into DQMH, we're just going to talk a little bit about something called actor-oriented design, just to understand a little bit more about why we might want to adopt DQMH as our chosen development architecture and framework. We're going to learn what it is, how it works, and how you can use it. And I'm going to build, at the risk of falling flat on my face, we're going to build a DQMH module live, so you can kind of see the productivity benefits and see that in action. So let's dive in. Actors and actor-oriented design. Now, when I say actor, I want to be very specific and very clear. This is not actor framework. We're not going to be talking about actor framework in this particular session, but we are going to be talking about actors and actor-oriented design. Actor framework is something that is an alternative framework, shall we say, to DQMH that allows you to carry out actor-oriented design. But as I said, we're not going to be talking about that today. I just want to make that specific point. We're not discussing actor framework. We are discussing DQMH. So actors, why? Well, hopefully everybody in the room is reasonably familiar with software engineering practices and understands that large monolithic applications are not really what we want to be building in 2026. So if I take an application there, an example, maybe my application controls some kind of fan. Maybe it's a wind tunnel acquisition system, as an example. It probably controls the fan. It probably logs some data. Maybe it also captures some images as well. But we don't really want to have an application that is monolithic in nature, in that there are no identifiable components within that application. So everything is kind of jumbled together into this one. I often refer to it as the VI. We don't want our fan code mixed with our logger code, mixed with our camera code, ideally, because it's maintainable, or reduces maintainability significantly. It's not scalable. So why is it not scalable? Well, it means that potentially, let's say we want to add a second camera. It means I've got to go in and start adding additional code and support architecture around that, and potentially interfering with some of the existing code around the logger or the fan, especially if it's this kind of monolithic, cluttered mess of LabVIEW code. It also means that it's highly coupled. So, for example, we've all worked on applications, I'm sure at some point in our careers, where we've wanted to make a small change to an application, and we've changed one part of an application and it's affected something else. And that's because these things are kind of coupled together and not isolated in their nature. In addition, it's not cohesive. So if I want to just test the logger part of that application, I can't do so. I've got to run the entire application. I can't just isolate the camera code, for example, or the logger code and test it in isolation and make changes independently of the overall architecture. What we really want are highly parallel modular systems where each function within that system is loosely coupled. So, for example, I've got a DAC component and it's responsible for just data acquisition. I've got a camera component and it's just responsible for integrating to the camera. It doesn't know anything about the fan. It doesn't know anything about the data acquisition. They can all be tested independently. They can all be modified and expanded independently. And that gives us this kind of modular design that allows us to work on these things with larger development teams without the risk of colliding with somebody else's code changes, and to make changes without affecting other parts of the application. So hopefully we all recognize that that is a more sustainable architecture going forward. So we're building these highly parallel modular systems. So just to define a little bit of syntax, when I talk about an actor, I'm referring to what somebody else might call a module. And I'll use those phrases somewhat interchangeably during the next 40 minutes or so. I'll also refer to it potentially as a process. It's something that is running asynchronously that has a very tightly defined scope. So if I go back one slide just to that, for example, I could think of my camera as being an actor or a module. It's running, it's acquiring camera data, it's doing something with that camera data, but it has no knowledge of the DAC, it has no knowledge of the fan, it has no knowledge of the UI, for example. It has a very specific function. These modules, these actors, they have state. So they have some kind of private data that they are responsible for and will persist. So, for example, the camera module, it might have some private data that refers to its address or its frame rate or the resolution, the number of bits, or the color depth. So it might have some information and it is responsible for the persistence of that data. If we want to interact with that data, either to retrieve something or to update that data, then we would need to interact with that module in order to affect that data. And how do we interact with these actors, these modules? We do that via message. In actor theory, messages are requests. They are never commands. So we would request, we would send a message to our actor, our camera module, requesting that it performs some activity. So I might send a message saying, hey, acquire a single frame. Because the actor has state, it knows whether it is in a correct state or configuration in order to carry out my request. It's the module, the actor, that is responsible for deciding, hey, Chris has asked me to acquire a frame. Am I in a state suitable for actually performing that action? So we're always making requests of our modules. We're never commanding them to do something, because ultimately it is the module that is responsible for determining if it can carry out that request. So just a little bit of syntax that goes along with that actor-oriented design. So what does an actor look like? It's a thing, it's a module, it's a process, it's got some private data, and it publishes an API, an interface, a programming interface that allows us to interact with it. So fairly straightforward. If so actor is a process, it has a very singular purpose. So it's a camera, it's a logger, it's a fan controller, it's a power supply, it's something, but it's a singular purpose that our actor has. It maintains some private data. It is responsible for maintaining that private data, and we can interact with it through an API. It receives requests, so incoming messages that we send to the actor are requests, and it can notify the world that something has happened, maybe some data has changed or that it's performed some action. It notifies us via the means of a broadcast. The actor itself decides if it should comply to the request, and really important, the actor knows nothing of the requester or the receivers of any of its broadcasts. So it doesn't know who is requesting that it should do something, nor should it, and it doesn't know who's registered to hear about the things that it might do, and again, nor should it. I heard a really nice analogy once that said, if an actor was a turkey, then come Christmas, we would ask it to cut off its own head. We wouldn't be doing that. We're sending a request to it and asking it to do something. So an example might be a power supply. We've got a simple actor here. It's a power supply. It has a public API. What does that API look like, or what might it look like? Well, it might have some requests, things that we can ask it to do, such as setting the voltage, setting the current limit, setting the output state, and some broadcasts, such as the instantaneous current measurement. So we can ask it, we can request that it does things like set the current limit, and it can tell us information such as, hey, the current being drawn right now is 50 milliamps. So that's how we interact with it through this public API. So just to kind of get that concept, so if we start to think about our applications as these different modules, these different processes, then we can start to modularize our application, and we can start to build in scalability, supportability. We've got individual modules that are uniquely testable, and they're isolated, so they serve a very specific purpose. We don't start blurring the lines where the power supply knows a little bit about the fan, or the camera knows a little bit about the UI. We don't want that. For maximum reusability and scalability, we want them to be isolated. So that's kind of the theory behind these modular applications. A little bit of glossary. So we've talked about a process, continuously running code. So almost always a VI with one or more loops. So we're going to just define some syntax, some terminology, so that when we actually dive into DQMH and do a demo, some of these words kind of make sense. So we've got a process, a continuously running code, a VI with a loop in its most simple form. Reentrancy, the ability for multiple instances of that same VI to run simultaneously. So we might have multiple instances of an actor. So if we've got a power supply actor and we need to control two power supplies, then we would like, ideally, we don't really want a copy. We don't want to have a second actor called power supply 2. We'd like to be able to launch multiple independent instances of the same actor and be able to control multiple power supplies. So reentrancy is a big part of this. An API. So when I talk about API, what do I mean? Well, I'm not a computer scientist. I'm a physicist, but to me, an API is effectively a programming interface. So we've all probably used the file IO API in LabVIEW, or the Q API, or even maybe the TCP/IP API, and they're a set of functions that simplify the thing that we're interacting with. So when we use the file IO API, we open a file, we write some data to that file, and we just pass it a string input, and then we close the file. The complexity of what's actually happening under the hood is hidden from us as the developer. We've been given a simple interface, and we interact with that simple interface. That's what we're going to do with our actor. We're going to provide a simple interface, and hide some of that complexity. And ideally, that API would also kind of carry out be organized in some kind of logical manner to allow us to use it easily and be more accessible. And then we've got the business logic. So that's the application specific code. So if I'm building a wind tunnel architecture, maybe there's some business logic that says the camera can't be turned on until the fan is spinning at a certain speed. I don't want that logic to be in my camera module, because that means then that that camera module can only ever be used in conjunction with a fan. What happens if I want to use my camera module in some completely different architecture? Likewise, I don't want the fan to be aware of the camera. So I need some kind of independent controller module that's responsible for looking at that business criteria, that business logic, and saying, well, the fan is up to speed. You can now start controlling and sending messages to the camera. So ideally, we would have very well-defined, documented places within our architecture where that business logic would be implemented, and we would try to avoid kind of muddying the waters by allowing the functionality of one module to leach into another, and likewise, business logic that's specific for this particular application shouldn't be in the modules themselves, because that then again limits their reusability on other projects. So synchronous process, that's basically when we've got an ordered operation it depends on completion of another process. So if we take the simplest example of the flat sequence structure, we can't carry out process B until process A is completed. Likewise, we can't carry out process C until A followed by B is completed. An asynchronous process is completely independent operations running in parallel with other processes. Process B does not depend on process A having completed, nor does process C depend on either of the other two. They are completely asynchronous and independent. Queues. We're going to be mentioning queues quite a bit in this presentation. So queues are simply a LabVIEW API for passing data within or between processes. So if I take that example there, we've got a very simple queue where we are publishing some data in one of the loops. In the top loop, we're on queuing some information, and that data, almost like a FIFO, that bottom loop has access to the data that's been published by the top loop in the order that it was published. So first in, first out, generally, although there are some functions within the queue API to allow us to bypass that and stick things on the opposite end of the queue. But typically what we would see is data being published in one loop and being received in a second loop via this queue mechanism. Typically, that is part of a design pattern known as producer consumer. One loop is producing data, one loop is consuming data. And then the final API I think that we're going to be looking at is the event API. And that allows us to pass data again within processes, but it's a little bit different in its structure in that it's event driven. So when on something happening, so when something happens, a button's pressed, or some data is updated, we can trigger an event. So in that example there, we've defined an event. In the top loop, we've registered to hear about that event. So we've set up this listener to kind of listen for that event happening. And then we've got our event structure, or our event handler that I like to think about, that will contain code to be executed in the case that that event occurs. So in the bottom loop, we generate the event, and the top loop would handle it. The top loop is where that event would be handled. Code would be executed to kind of take care of whatever we're wanting to do once that event is fired. So, a few more. I promise we're going to get into LabVIEW very quickly. I just want to make sure that some of this top terminology is covered. So, the design pattern, a theoretical mechanism to execute synchronous or asynchronous code. I'm sure we've all heard about producer consumer. Two loops, one producing data, another consuming that data. A state machine It's a design pattern. It exists in multiple different languages. State machines exist in C++, they exist in Visual Basic, C# and LabVIEW. They're a theoretical design to execute code either synchronously or asynchronously. And the queued message handler, of course. Architectures are real-world implementations of those design patterns. So, for example, the JKI state machine, probably the most well-known state machine pattern within LabVIEW, and that implements this theoretical mechanism of a state machine. There's also another one called TLB, top level baseline, which is more of a producer-consumer type architecture. And then there's Messenger Library from James Powell, which implements kind of an actor-oriented queued message handler design, although I'm doing it a huge disservice. It's way more complete and extended than that. And then we've got what I would call a framework, so a consumer-grade architecture. So that's not just a real-world implementation, but it includes documentation. It includes tooling to improve the developer experience. So in those cases, I'm thinking of things like DQMH, Actor Framework, JKI State Machine Objects, and workers. So these are not only architectures, but they include templates, they include tooling to allow us to actually build these architectures, and they include documentation so that we can support them going forwards. And of course, queued message handler is the one that we're really going to be focusing on now. So what's a queued message handler? Well, it's a project template. It's existed since 2012. Now, should say queued message handlers existed way before 2012, but in 2012, a design for a queued message handler was codified and was actually added to the LabVIEW project templates wizard, and kind of became this this architecture, this design pattern that people recognized. It became incorporated into the standard LabVIEW training offerings, such as LabVIEW Core 2. And I'm sure if any of you have taken any of the LabVIEW training, you will have seen something that looks very similar to what I'm showing on screen right now. So it is the official NI template for QMH. We've effectively got two loops. We have an event handling loop and we have a message handling loop that's shown there. And we utilize a queue mechanism for transferring data from the event handling loop, or the EHL, to the message handling loop. Why we might do that is because let's say we need to do some long-running tasks, some long-running operation, we don't want to block our ability to handle those events in the event handling loop. So effectively what we're doing is we're delegating them to the message handling loop. So the message handling loop would start to perform that longer running task, that operation, allowing our event handling loop to remain responsive to things like UI interactions, data being updated, user interactions, etc. If we want to communicate with the event handling loop, we can do that either via static events such as a button press or a value change event, but we can also interact with it using user events, as you see in that example there. So the stop button is registered as a user event, and then the event handling loop will respond if the stop button is pressed. It's a very standard architecture that we see in a lot of LabVIEW applications. So we got these two loops. The continuous measurement and logging example or sample project is built using the NI QMH, and I've used it many times. I think probably one of the first times I used it was maybe when I was preparing for my CLD exam a long time ago, but I see it day in and day out in my role in TSE with lots of different customers using it. So what's the problem with it then? Why do we not just all use NI QMH and be happy? Well, there's a few issues. Communicating between different QMHs is not straightforward. So I said, we want to have these different actors, these different modules, potentially multiple QMH, multiple queued message handlers within our system. Maybe one for a camera, one for a logger, one for the UI. and communicating between them is not straightforward. So what we actually end up doing is wiring queue references via the sub-VI connector pane. So if I go back for a second and we just look down at the bottom, we've got two additional message handlers. We've got an acquisition message handler and we've got a logging message handler. So we've got two additional QMHs there. And if we want to interact with them, we need to be able to access their message loop. So we've actually passed in references. If they want to send us information, we've actually passed in references to our queue. So now they have access to our queue on their connector pane, which means that they become less flexible. Those message handlers become less flexible because now we've defined as part of their connector pane that they should have access to this particular queue. Means that they're less reusable if I want to use them in a different scenario or a different situation. So they've got a queue reference on the sub-VI connector pane. Means communicating with them is less straightforward. So they're less scalable. They're difficult to debug when all queues are available to all message handlers, because now I've got the situation where multiple queued message handlers have the ability to on-queue data into each other's message handling loops. So when I see something happening in a message handling loop, I've got no way of knowing, well, who told it to do that? Where did that message come from? And if we remember what we talked about with actor theory, we interact with our module through an API, through an interface. Now, if we start to provide each queued message handler with access to each other's queues, we've got really we've kind of bypassed that. We've got no mechanism for knowing where did that message come from. It makes it very difficult to debug when we've got multiple queued message handlers in a large system. So no built-in mechanism to support multiple instances. So what happens to that situation where we want to add a second camera or we want to add a second power supply? Now I've got to create a copy of my queued message handler to talk to each power supply, because there's no built-in mechanism to cope with re-entrancy and to handle multiple instances of my QMH. And finally, adding frames to those event handling loops and message handling loops can be quite tedious. You've got to right click on it, add event frame, add the code to it. It means also that every time I'm interacting with it and adding capability, it's an opportunity for me to introduce an error. Okay, and that I want to avoid that as much as possible. So that brings us to DQMH. So its history. First public release was in 2015, developed by Delacorp. Like I mentioned, the alliance partner that I was with around 2012. LabVIEW Tools Network Product of the Year in 2016. There's now a community around it of people that are DQMH trusted advisors, meaning that they've been, shall we say, vetted, certified, that they are experts at using DQMH and maintaining DQMH-based systems and building code around DQMH. In 2021, the code was transferred from Delacorp. The IP was transferred, donated to the DQMH Consortium, a group of independent businesses. So that I think right now there are maybe 5 businesses making up the DQMH Consortium, and they are responsible for the stewardship of the DQMH source code. So when new features are added to DQMH, those features are added by the DQMH Consortium. They're responsible for providing support for DQMH if people have any technical issues, and responsible for actually managing and updating the code. Currently, it's being updated right at present. There was a new release recently. It's free to download and use. All you need is VI Package Manager, or you can download it directly from ni.com if you search for DQMH. But the easiest way to get up and running is by using VI Package Manager to download. Just search for DQMH, and you can go ahead and download it and install it into your LabVIEW installation. It's free to download and use. It's also the most popular third-party framework for LabVIEW in the world, with tens of thousands of downloads and tens of thousands of applications deployed into the world. I see it on a daily basis with my customers that I work with. There's a certification badge available from NI to kind of validate your proficiency with DQMH. Under the hood, it uses the same intra-process communication scheme as the NI-QMH. And when you see it in a minute, you'll agree it's very similar to that queued message handler structure architecture that I showed you a few minutes ago. It adds an inter-process communication scheme. So modules can communicate with each other, and that's part of the functionality that's been added as part of the DQMH changes above and beyond the standard NI-QMH pattern, and it implements that using user events. It's designed to be accessible by CLAD/CLD level programmers, minimal use of LabVIEW classes out of the box. So if you're not familiar with object-oriented LabVIEW, you do not need to be in order to use DQMH and be successful with it. It does use classes internally, but you do not need to use classes in order to use DQMH and be successful. So, a couple of terms. We're going to look at some block diagrams, some screenshots, then we're going to dive in and build a DQMH module and just see how straightforward that is. So the building blocks of the DQMH is the DQMH module itself. It's the core part of DQMH. It's an asynchronous process with a well-defined public API. So if we look at that little screenshot on the right, we've got a module. That is our DQMH module, our actor, our process. Remember, I'm using those terms interchangeably. In this case, I've got a DQMH module. It's called a timer. It's timer.lvlib. It's stored as a LabVIEW library. I'm not going to go into depth about this, but it can be the DQMH toolkit that you download from VR Package Manager allows you to create two types of DQMH module. You can create what's known as a singleton, which is a non-reentrant module, or a clonable reentrant module. A singleton means that if you try to launch multiple instances of a module, you will not be successful. You can only ever have a single instance of any given module in memory at any time. If you try to load a new instance of it, you will simply return a reference to the original instance. So they can only be, so if we have a fan and we're only ever going to have a fan, then one single fan, then I could create it as a singleton module. However, if I'm going to be controlling camera and I might need to have multiple cameras in future, then I would create it as a clonable module, which allows me to have multiple instances of my module in memory at any given time. Now, pro tip for somebody who's been using DQMH for over 10 years is to create your modules as clonable if you are unless you are absolutely 100% bet your house on it, sure that you're never going to have a second instance of something, create your module as a clonable. Even if you've only got a single instance of the module today, create it as a clonable if there is any possibility that in future you might have multiple instances. And I say that because one of the most heartbreaking questions in TSE that I get about DQMH is, hey, Chris, I created a singleton DQMH module to control something, and now I need two of those modules. And invariably my response is, I'm sorry, you're going to have to go and build that module again as a clonable module. And they say, can't I just add the parts to make it a clonable module? And the problem is that the work involved in doing that is significant and error prone and just to be avoided if you want to have a happy life as a LabVIEW developer, honestly. I would advise create it as a clonable, even if you only have one instance right now, and then be happy on the day when somebody asks you to add a second instance of that module. Only ever create it as a singleton if you are absolutely sure. And then don't ring up TSE and ask, hey, how can I turn my singleton into a global because you're not going to get a good answer. So messages, we talked about actors. How do we talk to them? How do we talk to our actors? Well, we talk to them via an API. We talked about the different types of message that we can have. Well, an obvious way is a request. That is a way for the external world to ask the module to do something. It's practically, it's carried out via means of a user event. It's implemented as a VI in the module's public API, and it can optionally include a reply for whoever makes the request. So we have two types of request. We have a request, which is simply, hey, module, do something. And we also have what's termed a request and rate on reply, which is, hey, module, do something. And I'm going to sit here and wait for you to tell me that you did it or that you didn't do it. But I'm going to sit here and wait for you to get back to me on that. So two different types. We can think of those as blocking or non-blocking requests. We're either asking the module do something, and then I'm going to carry on doing whatever I was doing before I asked it to do something, or I can say, module, do something, and I'm going to sit here and wait for you to get back to me and tell me, did you do it or did you not? Or did something else happen? But I'm still going to wait for you to get back to me. So we've got a request. And then we have a broadcast, a way for the DQMH module to tell the external world something happened. It's also a user event, and 0 or more external event structures might be registered to hear about it. But as I mentioned with actor-oriented design, actually the module doesn't care. I'm going to tell the world, hey, something happened. And I don't care if there's anybody listening or not. That's not my job as the actor. DQMH module broadcast that some people, other modules meet. So main VI is the main queued message channel of my module. We've also got something called an API tester. Now, I know I've talked an awful lot, and I'm not showing you any LabVIEW code. I promise I will. It's coming up really soon. But we've got this API tester, and the API tester is a VI that lets us test the public API of our DQMH module. It is probably, in fact, scrub that, it is the most used of DQMH, the ability to test the interface, the API of your DQMH module. Because we've talked about how our module has a very singular specific purpose. It should be highly cohesive in that it should only perform one task, and it should be loosely coupled. It should be independently tested. That API tester allows us to do just that. And then, honestly speaking, there's the magic of DQMH, which are the scripting tools. Under the hood, DQMH is really just a QMH module with some nice features implemented, and but under the hood, it really is a QMH. There's nothing about it, but the scripting tools absolutely are magic. Allow us to automate the generation of the module, the code generation, and the generation of that public API without us having to actually write the LabVIEW code ourselves. So it's automated for us using VI scripting tools. So when we've created a DQMH module, what do we have? In our LabVIEW project, we can see there, I've got module 1. That's my DQMH module that I've created. And you can see that I've got all these folders already created for me, a public API folder, a folder for broadcasts, a folder for requests, a private folder, something called module sync, which I'm not going to go into today, and then the main VI, our QMH main that we can look at. And down in the testers folder, we can see there's a test module 1 API tester as well, which we're going to have a play with in about 5 minutes time. So you can see that DQMH auto-generates, when I create a new module, DQMH auto-generates a significant amount of code for me in advance. There are tens, if not hundreds of VIs behind the scene that are scripted and generated. If I look inside, well, it looks almost identical to the NI QMH that I showed you earlier. We've got an event handling loop. We've got a message handling loop. There's nothing particularly scary about that. There's perhaps a little bit more documentation in there to explain explain to us what's going on, so that's super nice. But yeah, it kind of looks the same. My queue looks a little bit different. Well, that's because the queue is actually wrapped in a LabVIEW class. And I mentioned that you don't need to know about classes in order to use DQMH, but that they are used internally. And the reason for that is to simply prevent arbitrarily branching that queue reference and passing it all around the architecture and bypassing that that structure that we talked about, which is an actor has a tightly defined purpose and we interact with it through our API. We don't want to bypass that by just giving our queue reference here, there, and everywhere. So it's been wrapped in a LabVIEW class to prevent that. So we've got an event handling loop at the top. Events are triggered externally, but are registered for by this module and are handled by the event handling loop. So when something happens, the event handling loop handles it, and it may forward that that event to the message handling loop. So there we can see something happened and we're going to put it into that queue and we will handle it in the message handling loop. So I mentioned the queue. It looks a little bit different to the standard NWLVUG, but believe me, under the hood, it's still using the queue API. It's just been wrapped in a class to provide some protection to that queue so that it can't be abused and that reference provided everywhere. It also means that if you want to actually override that and provide your own child implementation, I'm not going to go into object-oriented programming, don't worry, but if you wanted to extend the behavior or change the behavior, you could do so without having to kind of touch the original underlying framework. You could provide alternative behaviors. Then we've got the message handling loop, the bottom loop, if you will, the bigger of the two loops. And this is where we might take care of longer running tasks that are delegated by that event handling loop. So we've just got two loops. It's a two-loop architecture, just like NWLVUG. So when something happens, we might choose to delegate it to our message handling loop. And I did mention right at the beginning that actors have state. They have private data. Well, in QMH, what does that look like? It's a cluster. It's a cluster passed around the message handling loop on a shift register. If we want to retrieve that data, or if we want to modify that data in some way, then we need to send a message to our DQMH module, to our actor, and ask it, hey, can I have the data? Or here's something new to put into the data. So it's just a type defined cluster that gets passed around using a shift register, and we need to interact with it by actually sending a message to the module. So that's the private data, and it can be super easily modified. We just need to double click on the type def and modify the data. So by default, DQMH ships with a single string within that type def that is called status. But if we need to add other structures to that, we can absolutely do so. And it's really easy to modify, as you'll see in just a few minutes now. So let's get started. Let's actually do some LabVIEW. So what I've got as a starting point is I've got a need to control a power supply. I need a power supply actor. I want to be able to communicate with my module, my power supply, and I might have one or more power supplies in my system. I've already got a driver. I went to ni.com and I downloaded a driver. And my driver, my simple power supply driver, has some functions. If you're a test engineer and you're familiar with power supplies, you'll recognize the ability to set the output voltage, the ability to set a current limit, turn the output on or off, and potentially measure the current being drawn by whatever's connected to my power supply. So I've got a very simple driver there. Now, actually, I don't have a power supply connected to me. I've cheated today. So all I've done is I've put a little bit of code inside to pop up a message whenever this VI is executed. So it says output state is off. If I turn that to true, it's going to say, hopefully, output state is on. That's great. So my driver's a little bit of a cheat today, but That's the typical kind of functions that we would want to carry out when dealing with the power supply. So let's create a power supply module. So let's open our LabVIEW project. And I'm going to create my first DQMH module. So I go to the Tools menu, DQMH Consortium, DQMH. You can see there's quite a lot of menus in here, but I'm going to go to the module and I'm going to add a new DQMH module. So I'm going to create my first DQMH module. I'm going to give it a name. Let's call it power supply. I can give it a description. And I should give it a description. It says it's optional, but I really should tell people what my module is doing. That is added to the descriptions of the library and the VIs. And it asked me, what type of module do you want to create? And remember, I said there's two. There's a clonable and there's a singleton. Notice that clonable is now the default, probably because there were so many people creating singleton modules and then getting really upset when they realized that they needed multiple instances and the sheer amount of pain and work that that involves. So I'm going to create a clonable module. I can choose to give it a different icon. So, you know, we could come into here and let's give it a different icon. Let's just put PSU and say OK to that. And there's a little tick box down at the bottom that says include do something events in this new module. These are simply example events, a request called do something and a broadcast called something happened that allow you to see how those events are, how they work under the hood. I'm not going to use them today, but if you're getting started with DQMH, it can be pretty useful to tick that box and include those example events. They can be removed later quite easily, but they can be quite useful, especially if you're getting started. So I think we've done everything we wanted to do. We've given it a name. I've told it to put it in a particular location. It's a clonable module. Let's say OK. And now some scripting is going to run in the background and work its magic. While that's running, you can make a donation to the DQMH consortium to keep doing their fine work with DQMH. And there we go. It's pretty quick. We've got some things appearing in our project already. We can see a module folder has now appeared with a power supply LVLib. If I extend that out, expand that, we can see lots of folders, and we've got an API tester. So let's just explore for a second. We have a public API. So this is the API that we use to interact with our module. And already we have some interface code that's been provided. So we have an ability to start a module. We can stop the module. We can show its front panel. We can request to hide its front panel. There's also, we can programmatically show its block diagram, for example. So there's already a little bit of an API been created for us to interact with that module. If we open its main, we can see it's this familiar QMH pattern that we talked about. So we've got an event handling loop at the top and a message handling loop at the bottom with lots of comments explaining what's going on in here, how it's working. There's some bookmarks that we can search for to find certain information if we want to know how to do something, for example. And we can see that there are certain events already in here, such as show the front panel, hide the front panel. Now, one of the motivations for DQMH originally was simply that lots of developers were building their own highly parallel asynchronous frameworks, and there seemed to be a huge amount of support tickets, support cases like, hey, my module starts, but when I try to stop it, it doesn't stop and it's left hanging and I have to use Task Manager or kill LabVIEW to get rid of it. When I have multiple instances, I can't talk to all of them. I can only talk to one of them. Part of the motivation behind DQMH was simply to create a module that out of the box would start, would stop, would show its front panel, and would allow you to have multiple instances. So that's why there's a lot of code there already. And then we've got this API tester. So this is the thing that allows us to interact with our DQMH module. So let's play around with our tester. This is just for test purposes, but I strongly urge you to use the testers. These are great, honestly. So if I start running it and I start a new instance of my clonable module, I can, out of the box, show its front panel, hide its front panel, show its block diagram if I want to show its block diagram, should I wish to do that. Super useful for debugging, by the way. And if I press stop, it will stop. My module has stopped running. I don't have, you can see, I don't have a running instance of my module. But it's clonable, so let's do that again. Let's run the module. Let's show its front panel. Let's start another module instance. I've now got 2 modules. If I look on here, in fact, let's do 3. I've now got 3 modules running. Let's just show the front panel of module number 3. There it is. Let's show all of their front panels. You see, I've now got 3 instances of my module running. I could choose to hide them or just hide one of them. And I might choose to stop just one of them. So let's stop module 4. Let's check. There's only 2 running now. Yep, there are. Now, finally, let's stop all of them. So out of the box, it's behaving just like a QMH, but out of the box, it's guaranteed that it will stop, it will start, and I can have multiple instances of my module. My module doesn't do anything particularly yet, apart from hide and show its front panel, but it's kind of ready to run, ready to rock and start writing some code. So let's make our power supply module, let's make it do something useful. Let's show a little bit more about DQMH. So we've stopped all of our modules, so we can stop the tester and close it. So the first thing I want to do is I want to be able to set the voltage of my power supply. So I need to create a public API method, a request to ask my power supply, hey, set the voltage to some amount, some value. So we go to tools, DQMH consortium, DQMH event, and we need to create a new DQMH event. If we had multiple DQMH modules, they'd be listed there. We only have one at the minute, which is my power supply. And it asks us what type of module, what type of event, what type of message, if you want to think of it as a message, do you wish to create? Do you wish to create a request? So that's me saying, hey, module, do something. Is it a broadcast where the module tells me that something happens? Is it that blocking event that I talked about earlier, which is, hey, do something and I'm going to wait for you to tell me that you did it? Or is it the round trip, which is a much rarer use case, which is, hey, do something, I'm going to wait for you to tell me that you did it, but you should also broadcast that in case anybody else cares about it. So in this case, I'm going to create a request. I want to ask the power supply, set your voltage to 5 volts. So let's give it a name. Let's call it set voltage level, and let's give it a description because we're a good developer. So we try to give descriptions to all of our functions, our methods within our module. So set the voltage level as desired. Now over on the right, we've got this thing called the events argument, the event arguments window. Our request has some data associated with it. We can't tell it, hey, set the voltage level without telling it what we want to set the voltage to. So we're going to be providing some numeric data along with our request. So here's where I define the data type. So I'm going to create a numeric control. I'm going to call it voltage. So now I need to create this event. So I simply just say, okay. And the DQMH scripting does its thing. And you can see a bunch of codes opened up. And the first thing that gets opened is the tester. And that should give you a hint as to how important the tester is. So it's created some code already. And it tells me code needed. This is where you need to actually position the set voltage button appropriately on the new front panel. So there's a set voltage level button here that's going to allow me to set the voltage. I'm regretting not having my mouse today. So let's put that button there. And we need a numeric indicator as well. So let's create a numeric indicator to actually define, sorry, a numeric control to actually define that voltage level. So there's our voltage. We could have done it on the value change event, but let's leave the Boolean in for now. And let's wire that up. So we should see that, look, there's an input waiting for us. It tells us there's an instruction that's been written saying position the set voltage button appropriately and then delete this label when done. So I'm going to wire that up and delete that as I've been told. And let's save and close our tester. So that's my tester for setting the voltage level. If I look at my DQMH main, it's created event cases for me already called, event cases called set voltage level, and it's created a message handling case. This is where I actually do the work that says set voltage level, and there's an instruction code needed. Configure the message case for handling the set voltage level. So this is where I actually do the stuff, actually talk to my instrument and set the voltage level. So this is where I might actually choose, hey, I want to call my my power supply driver and set the voltage level. So set output voltage. Let's call my driver function. It's got an input which is voltage level. Let's wire that in, and I've done my bit. Now, of course, in practice, there might be instrument visa references and things like that to deal with. But right now, I'm calling my driver. That's just going to pop up a message for the time being. So let's close that and save our DQMH module. And let's go back to our tester. And let's run our tester again. Let's run our module instance. Let's show its front panel. There we go. Let's hide that over there. And let's set the voltage to 5 volts. And we're going to request that it sets the voltage to 5 volts. And it called our driver function and it set the voltage to 5 volts. I could now run another module instance and let's set the voltage on my other power supply. Let's set that one to 4. So I've set one of my power supplies to 4 volts and I set one of them to 5 volts. And if you think about the amount of code that I've actually written, I think I've joined 2 wires up so far, and I've now got a module that allows me to have multiple independent running instances of my power supply module talking to 2 different power supplies, and I can command them, sorry, that was a bad use of the word command. I can request that they do things independently. So we've asked our module to do something. Let's ask it to do something else. So let's stop all instances and let's ask it to do one more thing, and then we'll create a broadcast. So let's ask it to set the output state. So let's do DQMH event, create a new DQMH event, power supply request, set output state, and we know that that's going to be a Boolean. I'll just go a little bit faster. So let's have that as a Boolean. Quick description, and let's say OK. And there we've got a button. Actually, I think I'd like to replace that this time. So let's replace it with something a little bit more like a power supply. Let's replace it with a push button. Let's show its label, and we can simply wire that in. That's our tester written. So our tester can test that functionality. And on the block diagram here, we can see set output state. It's asking us for somewhere to implement the actual setting of the output state. So I'm going to call my driver VI again. Did I not bother to? Was I a terrible developer? I was a terrible developer when I wrote that driver VI. Fortunately, LabVIEW's pretty quick, so let's just add that to the component really quickly, and let's implement our setting of our power supply state, output state. So let's run our tester again, and then we're going to create one broadcast event. before we kind of wrap up. So we run a module instance, we can set it to 5 volts, it tells us, and we can do things like we can set the output state on, we can set the output state off, and if we had multiple instances of the power supply, we could set the voltage levels independently and have multiple instances of power supply. So it makes it super easy. And this is just a power supply module. So I've now got a module that I can reuse on different projects because I'm not going to contaminate it with any application-specific implementation or any business logic. Its job is to be a power supply module to control and talk to a power supply, and it's an independently testable component. So DQMH allows you to very quickly create those independently testable, highly cohesive components. So one more event before we kind of summarize the benefits of DQMH. Event. Let's create a broadcast. So let's create our broadcast and let's call it current measured. And we know that the data type, we know that if we measured the current, then we've got some sort of numerical value to tell the world about. So let's just try dropped it in the wrong place. Let's see, LabVIEW is so much nicer with a mouse, isn't it? So let's call that current measure, and let's create our broadcast event. So now we've got a broadcast event. It's told us the tester's been created for us already. So let's just move these things here, and it says broadcast response received. So let's change that to say, instead of saying response received, let's change that to say current measured. And we know that it's going to be a numeric. It's going to hopefully be a floating point. And if we look at the event terminal here on the left, if we right click on it and say select item, you can see it's created an item for me that contains that measured current. So the data appears when we measure the current will appear in my event terminal. So anybody who's registered for broadcast from my DQMH will be able to have this really convenient way of just accessing the data that's being broadcast via the event terminal. So there's my tester. We've added a message to say the current was measured. So here on the block diagram of our DQMH main, there's our broadcast that we can put somewhere appropriate for broadcasting that the current's been measured. I'm going to cheat a little bit just in the interest of time because I know I am running out of time. I'm going to just create a timeout and say broadcast to the world what the current is every let's do every 5 seconds. Let's broadcast to the world what the current is. Okay, so every 5 seconds we are going to broadcast to the world. So let's measure, let's get our current measurement. Let's measure the current. Let's drag that in. Oh, I didn't like that, did you? Let's just select it. Measure current. So we're going to measure the current using our power supply driver. I've done the same trick again, haven't I? Forgot the campaign. There we go. Pro tip, don't forget your campaign. So we're going to measure the current. We also need to provide something called the module ID. So that's just the address of the module that's actually broadcasting the data, that's broadcasting this information. We can achieve that by accessing the module admin data. There's instructions on doing all of this in the DQMH help, which I will show you in a second. So every 5 seconds, we should broadcast to anybody and everybody who's listening that the current or what the current actually is. So let's run that API tester again. So run a new module instance. After 5 seconds, we should see a current value appear in our status. There we go. So every 5 seconds, that module is now going to tell me what the current, it's going to measure the current, and it's going to broadcast it to anybody. I can still interact with it. So let's set the voltage. Let's set the voltage to 7. Yeah, you see, I can still interact with it. I can still turn the power supply on, but it is still going to broadcast to me every 5 seconds that I have got a current measurement. So I've now got this really neat, without me actually doing an awful lot of coding, I've now got this really neat module that I can control. I can send it requests. I can have multiple instances of my module, and it can also broadcast information when things happen. So let's stop that running. So let's go back to the slides just to summarize. So we created a DQMH module. So a couple of points before we kind of wrap things up. So if you're a DQMH module developer, so I've just fulfilled the role of a DQMH module developer. I'm the one creating the requests and the broadcasts. I'm defining what the API of my DQMH module should be. So I've just created a power supply module and defined that I should be able to set the voltage. I should be able to set the output state, and it should tell the world what the current is every 5 seconds. I defined that, and I'm the one that's writing the kind of the business logic of power supplies in that module. So I might do something whereby, you know, if the measured current is above a current limit, then I turn the output state off. Hopefully I've bought a decent power supply and it does that for me already internally, but maybe it doesn't. So in which case I probably want to keep reading the current, and if that current goes above a certain level, I probably want to turn the output state off or start regulating the voltage. So I'm the developer. That's my responsibility to do that. It's also my responsibility to keep the API tester up to date. I think the API testers are a fantastic way of actually getting to know a DQMH module, find out how to use it, and actually play around with it individually. Definitely use the scripting tools. So to 3 events or 3 is 2 requests and 1 broadcast. I use the scripting tools to do all of that. Don't manually try to build the functionality. Use the scripting tools for creating those messages, and document as much as you possibly can. So the module description, the event description, document. You'll thank yourself for it in 5 years' time when you come to reuse this DQMH module. If you're a user, then as a developer, I'm just going to use the public API, the requests and broadcasts of a DQMH module. So if I just return really quickly to the code, if I close that, I'm now going to use my DQMH module as a test developer. I can simply do something where I say, okay, start the module, show its front panel, set the voltage level, set the output state, And this is, as the developer of an application, some sort of test application, I can just utilize these VIs to actually perform the task that I want to do. So if I join these together, schoolboy error, not having a mouse. Apologies for the wiring. This does not reflect I will normally write code. So let's create a constant and let's set that to true. Let's set that to 9 volts. One other VI that we needed in there, which was the synchronized module events. So let's delete that one. Let's put that there. Should have put that in between those 2. So I'm now the user of the DQMH module. So somebody kindly wrote me this power supply DQMH module, and I'm now going to use it to set the voltage and turn the output state on. So if I run this, and I've shown its front panel as well, so if I run this, it should launch a module, show its front panel, set the output, and set the voltage level. So there we go, set the voltage to 9, turn the output on. So that's, I'm now interacting with my DQMH module, my process, my actor, if you will. So that's me using it as the end user, as a user of it. So I'm using the public API of my module. So benefits, really quickly, scripting tools, absolutely, will save you hours of development time creating new requests and broadcasts for your module. And if you keep your API tester up to date, that will also make debugging far, far easier, because your module should be individually and uniquely testable, and it should have a very specific purpose. QMH is a very familiar pattern. If you've done the CLD, if you've taken your CLAD, if you've taken any of the LabVIEW Core 1 and 2 courses, you should be familiar with the QMH design pattern anyway. So looking at the block diagram shouldn't be intimidating. You should be able to very easily understand what is actually happening there. The module starts when you ask it to start. It stops when you tell it to stop. There's some basic error management in there, although you can absolutely extend that and build your own error handling strategy. As you've seen, it can show the front panel and hide the front panel, so it's got some basic front panel management. There's tools for debugging, there's the API tester, there's the ability to show the block diagram. If you've got multiple reentrant DQMH modules, being able to show a specific block diagram is super useful when it comes to debugging. If you've ever debugged reentrant clones, you will know what I'm talking about there and appreciate it. How do you learn it? So there's so many topics, an hour really is just barely scratching the surface. I haven't really talked an awful lot or shown you about request and reply events. I haven't done a deep dive on the clonable modules, something called helper loops or private events or local instance events. I haven't even begun to talk about things like hardware abstraction layers, best practices, or any additional tools that build on top of DQMH. So where do you find out about those things? Well, if you're interested in DQMH for hardware abstraction, there's a blog post there. I was just looking at it actually. I wrote it 15 years ago. So there's a really interesting blog post on using hardware abstraction layers inside your DQMH. There's the DQMH documentation. The documentation that ships with DQMH is super extensive. So if you look at DQMH Consortium, DQMH Help, you will see documentation that is embedded here that is huge. There's a huge amount of documentation and videos showing you right from first principles, getting started, through to advanced techniques with DQMH. There's a lot of content on there. Tom McCullen did some excellent online videos there on YouTube, so there's links in this slide deck that I will circulate after today, or your organizers will. John, I'm sure you can do that. But Tom did some excellent videos about getting started with DQMH and deep diving how it works. They're on YouTube. Urge you to strongly recommend you to go and look at those. There's a bunch of videos from the DQMH Consortium as well. Shipping examples, so there's a thermal chamber example whereby you've got multiple DUTs under test and you want to test them in parallel, but you've got one thermal chamber, so you want to do things like ramp to a temperature, and only when you get there do you want to start testing. That's kind of a nice real world use case that I think kind of really highlights the differences between singleton and clonable. There's an official DQMH training course. There's the hardware abstraction layer. I still get questions about that particular blog post 15 years ago, so I'm guessing it was pretty useful. So I appreciate that has just been an absolute fire hose of DQMH content. You probably sat there and it's just been like, Chris has just been throwing and talking DQMH for like the last 50 plus minutes. So I'm going to stop talking now and throw it open to any questions, any comments. Over to you guys.
Yeah, so we might have time for like one quick question, I think.
Yes. Sorry, John.
That's all right. I appreciate the depth you got into there, Chris. I think David might have dropped a quick question in the chat if you're able to just see if I can bring that.
Let me stop. I'll stop sharing and I'll look up. Okay, so David's asked, my concern with frameworks such as DQMH is that people start to see them as the only solution. Absolutely. So they absolutely fall into the kind of this is a pretty good hammer, suddenly everything looks like a nail category. And I've seen people trying to use both DQMH and active framework for problems that can be solved with a state machine. I'm very much a kind of a defensive programmer. If you think you can solve a problem with a state machine, I would tend to kind of solve it with a state machine unless there's some future scope creep or something like that. But absolutely. How do you recommend the process of selecting a framework? The first thing I look at is who's going to use it. If I'm delivering a solution into a company, an organization, and they have CLA D, beginner 6-month experience level developers, I would be a poor engineer to deliver an active framework solution for them because they won't be able to support it and they'll be horribly confused by what they see. So the first thing I look at is who's going to use and support this application, who's going to extend it in future. I think that's really probably one of the primary things that I would look at. If it's myself looking at it, then the next thing I look at is, okay, is the hardware ever going to change? Do I need scalability? Do I need objects? Do I need LabVIEW classes? If I do, then I might look at something like Active Framework. But again, I'm going to be mindful of, am I time constrained? Is there likelihood of doing a lot of debugging? Then I might tend towards something like DQMH. But the primary thing I would look at is who's going to be using it, who's going to be supporting it. But I would urge, I had a conversation, I'm aware of time, so I'll keep this really brief. I had a conversation with a developer recently who said, I can't wait for my next project, I'm going to use DQMH. And I asked them, okay, what's your next project? And he said, oh, I don't know yet. And that set up alarm bells for me because you've arrived at the solution before you've even understood what is the problem you're trying to solve. I strongly urge you to look at the problem and understand, does it need asynchronous modules? Is it going to be supported by a less experienced developer? Does it need to be scalable? And I think you need to look at those things first before you even start to research which framework solves these problems. I hope that kind of answered your question a little bit, David.